Hello dear student, welcome to EPG Pathshala. I am Anshul Srivastava from Department of Physics, Faculty of Science, Banaras Hindu University. Today we are going to discuss about the module which is on synthesis and purification of carbon nanotubes from the paper Nanoscience and Technology Second. After studying this module, you shall be able to understand the following things. You can know the different synthesis technique of carbon nanotube such as arc discharge, laser ablation and chemical vapor deposition. You will also know the possible growth mechanism of carbon nanotube. I want to give some more recent development on the synthesis techniques of carbon nanotube such as patterned growth, alumina template and microwave assisted growth. And finally, you learn the purification techniques used for nanotube purification. As you know that the discovery of carbon nanotube was done by Sumo Ejima in 1991. He is a Japanese scientist, microscopist. And this gives a great interest both at a fundamental point of view and for future application. Carbon nanotube is one form of carbon with nanometer size diameter and micron to millimeter length, and their aspect ratio is quite high. The atoms are arranged in hexagons as same arrangement in graphite, but they consist by rolling of this graphitic sheet in form of cylinder. One sheet of graphite is known as graphene. When they roll up into a seamless cylinder, will form a nanometer diameter carbon nanotube. Carbon nanotube has attracted the fancy of many scientists worldwide. The unique and unusual property of this structure makes them a unique material with a whole range of promising applications. CNT does not occur naturally and therefore it can be produced in the laboratory. There is a need of development a synthesis technique where economical, feasible, large-scale production and purification techniques can be developed. Different type of carbon nanotube can be produced in various ways. Carbon nanotubes are discussed in this module in terms of their history, type, structure, synthesis and characterization methods. And commercial application of CNT has been rather slow to develop, however, primarily because of their production cost of the best quality CNT. The relatively low yield, high operational cost and low throughput of these methods limits their potential use as a manufacturing approach for large-scale nanotube production. The commercial use of carbon nanotube in real-world applications required a cost-effective method to fabricate large amount of nanotubes with desired material property. So, the present module is aimed to discuss the different synthesis approach for obtaining good quality single valve carbon nanotube and multi-valve carbon nanotube. So here I want to discuss the method by which we can synthesize carbon nanotubes. As you know, carbon nanotubes does not exist in nature. Therefore, we have to synthesize these materials in laboratory. The main techniques which produce carbon nanotubes are: the first one is arc discharge technique, second is laser ablation technique, and the third one is CVD, which is full form is chemical vapor deposition technique. So let us go to the first one, which is arc discharge technique. So in this technique, the person who first involved in producing carbon nanotubes are Professor Ajayan and Professor Ibesen in NEC, Japan, in the lab of Sumo Izuma, who is the inventor of carbon nanotube. So, how one can produce carbon nanotube through arc discharge? In this case, we have to take graphite rod, two graphite rod. One graphite rod can be sharpened for better current density, placed together a millimeter apart, and apply a DC plasma so that carbon will vaporize and form hot plasma, and at cathode this deposition of soot and carbon nanotube takes place. This need around 100 amperes current and few volts like 10, 20 to 30 volts. Typically, the yield is around 30% to 90%. There is a possibility of tuning of single valve carbon nanotube and multi-valve carbon nanotube depending on the arc condition. As you know, carbon at high temperature make carbon dioxide. Therefore, we need a chamber in which we put helium or argon gas. These are the inert gas which does not allow carbon to oxidize. If we do this measurement, if we do this synthesis, then we end up getting carbon nanotubes through arc discharge technique, and purification can be made 100% carbon nanotube, which I will discuss later. The MWCNT mostly is of a smaller diameter from 1 to 10 nanometer, and outer wall depending on the thickness of the wall. So if it is like 10 valve of nanotube, then per wall 3.4 angstrom increase will take place. So one can see by transmission electron microscope that how thick or thin nanotubes has been formed. The production can easily produce single valve carbon nanotube and multi-valve carbon nanotube. For producing single valve carbon nanotube, we need some metal catalyst which allow them to grow on top of that. In multi-valve nanotubes also we need catalyst, and sometimes it is without catalyst also it is possible. Since this arcing is taking place at very high temperature around 3 to 4000 degrees Celsius, therefore the defects are very less in arc discharge nanotubes, and therefore they are very inert in nature. Here I want to discuss the laser ablation method. This method was developed by Smalley, who is one of the Nobel Prize winner in case of fullerene from Rice University, Houston, USA, and who developed this method in 1995, where he blasted an intense laser pulse on graphite with a very specific environment, and this laser pulses has generate electricity and carbon gas from which the CNT will form. Trying various conditions until hit on one that produce prodigious amount of single valve carbon nanotube. The typical yield in this case is quite high, and it is around 70%. This single valve carbon nanotube, known as SWCNT, forms in long bundles of tubes which is 5 to 20 micron of size with individual diameter from 1 to 2 nanometer. So this method is really give a very good quality single valve nanotube with the yield of 70%. Multi-valve carbon nanotube, not very much interest in this technique. Multi-valve carbon nanotube was not of very much interest in this technique because this is expensive, and synthesis, however, synthesis is possible in this case, but there is a difficulty because of their cost. Production of single valve carbon nanotube with fixed diameter control with a very small defects will be a very good for using this technique. One can find out. Defects are very less in this case because this is happening at high temperature process. Chemical vapor deposition technique. This CVD technique has been introduced by Japanese scientist Indo from Nagano in 1993. He put a substrate in an oven, heated this up to 600 to 900 degrees Celsius, and slowly passed the carbon bearing gas such as methane. The carrier gas can be used as argon or nitrogen. As gas decomposes freely up to carbon atom, it recombines and forms CNT. There is some catalytic material also placed so that the growth can be increased or growth can be started. Nucleation can be taken place. The typical yield is around 30 to 100%. Single valve nanotube is long diameter and ranging from 0.6 to 4 nanometer, and length will be in couple of hundred of micron. The multi-valve carbon nanotube ranging from diameter to 10 to 240 nanometer, so there is a possibility of growing thick MWCNT in this case. It is very easy to scale up to the industrial product in this case. The length of the nanotubes are quite long. This process is simple, and single valve carbon nanotube can also be controlled and produced effectively. Therefore, this is a very reliable low cost method to grow bulk amount of single valve carbon nanotube and multi-valve carbon nanotube. Since this process is taking place around 900 degrees Celsius, therefore they have quite large defects in the CNT. This is some way good as well as bad. If you want to functionalize it, it is good, but if you want to find a pure defectless tube, it is not very nice. So I discussed this chemical vapor deposition technique, where I want to discuss the spray pyrolysis technique for synthesis of mostly MWCNT or bulk microstructure, which is made up of carbon nanotube or multi-valve carbon nanotube. In this case, we use a tube of silicon dioxide, a smaller diameter silicon dioxide tube, where we put argon as a carrier gas, maybe some percentage of hydrogen also in mix so that oxidation will not take place, and use xylene vapor mixed with ferrocene and spray this with a specific nozzle inside the furnace, which is heated around 1000 degrees Celsius. What we get? We get a tube structure which is bulk tube, very visible in this slide, where you are able to see that 12 centimeter long tube structure has been built. This tube is hollow in nature and bulk size tube. You can see that the radial alignment of carbon nanotube. We break this tube and put it in the microscope, and we have seen that our tubes are aligned radially along the thickness of the bulk tube. This jungle of a bundle of nanotubes are very much of good quality. Once we developed a method to grow a bulk tube which is made up of carbon nanotube, then we have tried to make many layers of nanotubes. In slide number 15, we have shown there is a 4-layer of aligned carbon nanotube. Every thickness of every bundle is around 100 micrometer. If you zoom it and see, then in the right side, one can see that very good quality nanotubes bundles has been shown. The bundles of every thickness is around 100 micrometer, which is self-standing, and wall has been constructed using this carbon nanotube. So this is a new method by which one can produce a bulk tube which is made up of carbon nanotube and can be used for many applications like filter and others. Now in slide number 16, I want to discuss how this nanotube will form. As I discussed you that we send a carbon based material inside the furnace and with the nanoparticle or the metal particles along with that as a catalyst. So what will happen? The metal particle will deposit on the substrate, and then at high temperature this metal particle has capacity to dissolve some carbon. Once some carbon is dissolved in the matrix, and if it cool down, in that case this carbon should come out at room temperature. This carbon will come out at the room temperature in form of tube because they are energetically favored. There is a two possibility that catalyst is sitting on the substrate, and there is another possibility where this catalyst can come up on top. Growth is possible. So there is a two mechanism by which one can understood that how nanotubes can be grown. What are the other method to grow single valve carbon nanotube and multi-valve carbon nanotube? There is a method known as pattern growth, in which we first prepare the substrate. This is required for many applications where we want the growth of nanotube in a specific position, not everywhere. So in that case, we have to pattern our substrate in such a way that carbon nanotube should grow only where we want. This patterning can be done using photolithography or electron lithography, where we put our catalyst particle in a desired position and allow this substrate in the furnace to grow carbon nanotube. Depending on the particle size, the tube can be single valve or multi-valve. There is a many research done in this field, and people has optimized the condition to grow good quality single valve nanotube as well as multi-valve nanotube in a very specific position. This method allow to grow nanotubes at their desired position. Now let us discuss another synthesis technique, which is alumina template method. In alumina template method, there is commercially available alumina template with different pore size. This pore will decide the diameter of nanotube. So depending on the need of your diameter of nanotube, one can buy this alumina template from the market. However, it is possible to grow this alumina template in your laboratory too. This is out of scope of this particular lecture. However, those who are interested can read the research paper of growing alumina template. This alumina template can be used to grow carbon nanotube. This works as a substrate, and again with a very similar method which we have discussed in chemical vapor deposition, one can put this template inside the furnace to grow carbon nanotube. Mostly this alumina template method nanotubes are open-ended in nature, which is very specific application. One can put any metal nanoparticle or anything which of desired need inside the tube you want. For example, you can put platinum, nickel, which act as a catalyst particle and used in fuel cell or many other energy application. So this particular template, alumina template method is very useful for growing a different kind of nanotube and can be used for many applications. Finally, there is a new method developed recently where one can grow through microwave synthesis nanotube. This synthesis technique allows you to grow huge amount of nanotubes in very small time. You can put the organic solvent along with ferrocene in a microwave and heat it, and you will end up reasonably good quality nanotubes in few minutes. So this is another method recently developed to grow different multi-valve carbon nanotube. So I discussed here there is a few very renowned methods as well as few other methods to grow carbon nanotube. When we produce carbon nanotube, there is a many other contaminants present in the sample. Therefore, we need to purify this carbon nanotube. Purification of carbon nanotubes generally refers to the separation of this carbon nanotube from other entities such as carbon nanoparticle, amorphous carbon, vitreous carbon, reduced residual catalyst, and other unwanted species. There is a many methods where one can purify this carbon nanotube, but three most important one is listed here: the gas phase purification, the liquid phase purification, and intercalation method. Let us discuss the gas phase purification. This is the technique which was developed by Iveson and co-worker. What they did in this process, they heat the carbon nanotube in presence of oxygen at a very fixed temperature so that the other vitreous carbon or amorphous carbon which evaporate first and leaving behind the carbon nanotube. These workers realized that nanoparticles with their defect centers might be oxidized more rapidly than the relatively perfect nanotubes, and they found significant relative enrichment of nanotube could be achieved by this way. There is a drawback that along with this nanoparticles, we cannot remove metal nanoparticles, and Therefore, we need another method for purification of metal nanoparticles which is coming from the catalyst. This can be done using liquid phase purification technique. In order to overcome this limitation, liquid phase purification that always simultaneously removes both amorphous carbon and metal catalyst. In amorphous carbon, and if we use acid, then in that case the metal will dissolve and amorphous carbon also make salt dissolve or actually react and find with water or with this solution come out, and finally we will get a purified nanotube in that case. Let us talk about the intercalation method. This is an alternative approach to purify nanotubes, was introduced in 1994 by Japanese group. This techniques made use of the fact that nanoparticles and other graphitic contaminants have relatively open structure and can therefore be more readily intercalated with variety of materials that can close to the nanotubes. So, students, here let us summarize what we have learned in this module. In this module, I discussed the production method, the synthesis method of carbon nanotubes, which includes arc discharge method, chemical vapor deposition, laser ablation method, and some other new methods. We have also discussed all the techniques for purification, including gas phase, liquid phase, and intercalation, and one can get a very good quality purified nanotube in this way. As a result, they may be changed in the electrical and mechanical property and actual structure of CNT. Therefore, the main thrust of the research should be in the area of producing and purifying CNT in a single and efficient step process to conserve the fascinating features of CNT. Thank you.